Hello, this is Alan McKay, and I'm here to present on the undergrad research I've been conducting with Dr. Burns throughout the summer and into the fall semester. We've been taking a look into the population protocol, which is a relatively new model of computation. This includes taking a look at what has been set in place pertaining to the model and how it can be expanded for practical usage. What is a population protocol? As mentioned, it is a computational model. Pictured here are two models we are all familiar with. The Boolean circuit model is what most think when symbolizing the utility that a modern computer gives us. And in classes such as theory of computation, we study the Turing machine. Through it, we are given the opportunity to take a look at another abstract representation of how one can store data and apply functions to that data. We learn that the Turing machine is able to execute the same set of functions as the Boolean circuit model. This notion of abstract representation is a key facet to what we study in the computer science department as we learn different programming languages and the paradigms they are part of. The population protocol differs between these two models in the sense that it was motivated by distributed computing. The problem was posed that if you give a flock of birds a set of very simple sensory tags which are able to communicate with each other, and each sensor will set a flag if an individual's temperature reaches a certain threshold, is there a means for the population to know if one of the birds has met this criteria? The population protocol is a way to solve this problem. The model is composed of a group of identical finite state machines acting as agents that interact in some way. Their acceptable values are represented in the set Q. A transition function describes what happens when two agents interact, which is represented by delta. And the other pieces consist of an input alphabet sigma, an input map which primes the states of each agent, which is represented by iota, and an output map which is represented by omega. A population protocol works as such. Two agents randomly interact. One of the agents initiates the interaction, noted as the sender. The other agent is the receiver. The two agents each have a state prior to an interaction. The combination of these states form a tuple as an index in which the transition function is accessed. These agents then change their state to the result of this access. The figure here sort of represents the execution of a simple protocol. Let L represent a state where an agent hasn't met that certain condition, and let H represent the state in which an agent has met that certain condition. The transition function describes whether or not two of these interacting agents have met this criteria. So if we take a look here, this first step assumes that this agent whose state is H interacts with this agent whose state is L. They form a tuple based on this information, which in this case is H and L. We access the transition function, and we conclude that the first agent's, the sender's agent's state remains H, while the receiver's state changes to H, and we see that here. And you could sort of walk through this process in terms of this execution. And thus we can see that the population propagates the idea that there exists an H state, and eventually it converges on it in the sense that all the agents have their states changed to H. This is under the assumption that there is a loose fairness condition where a set of agents do not needlessly interact with each other, generating fruitless results. This fairness condition is always assumed when analyzing algorithms for population protocols. It should also be noted that this execution that we see before us right now is one of an infinite amount of executions that occur. Indeed, for between step 1 and 2, it could be that this agent, whose state is L, interacts with this agent whose state is L, and they could sort of communicate and nothing occurs because, as we can see from this tuple right here, L and L, that their states won't change. You may notice that this function is essentially a Boolean operation. Just consider each occurrence of L to be a 0 or a false, and each occurrence of H to be a 1 or a truth. A population protocol can be used to solve the other Boolean operations. As it turns out, the population protocol is able to solve the set of functions described with Presburger arithmetic. From this, various sets of algorithms have been conceived for this model, such as leader election protocols, where the agents work together to elect a leader who can then carry out special tasks. There are protocols which spread epidemics to the population as a whole to give the population a sense of a program counter. These are all examples of protocols that Dr. Burns and I have wanted to explore and analyze. One means to analysis is simulation. The figures you see here were output by an ad hoc simulator I built late in the summer. This prototype acted as a means to explore some of the features that should be present. The simulator also produced output of heat maps for interactions that I've dubbed null. And null interactions are those interactions I mentioned earlier in which the states of the agents don't change. Getting a good look at these heat maps can help us improve upon the various algorithms being executed in population protocol, and it's a good ways of finding a means, it's a good means of finding potential bottlenecks that may occur within a graph of a population. One major flaw of the simulator that I built, though, was it only handles bidirectional graphs. You don't see any arrows on these edges right here. In the flock of birds scenario I shared earlier, it is a good example of a protocol where each agent is fully connected, and the edge between the two agents is constantly in flux as the birds move towards and away from each other. But we may want to examine situations where not every agent is fully connected, and we may also want to examine situations where the population graph has one-way communication. It should be noted that one-way communication is a concept that exists within the scope of a population protocol. If we look at this Boolean OR operation effect here, if we were to take out this second rule within the transition function, it would still converge on the fact that there exists an H value within the population. It would just take more time. More of those null interactions would occur, because basically what this state is saying is if the sender's state can change dependent on the receiver state. That's all it's conveying right there. So once again, if we were to take that out, it would still converge. It would just take longer. That's besides the point, though. A population can be represented by a graph. Thus, I ended up making a set of parsers. I guess I should say that I ended up rebuilding the simulator from scratch that I sort of laid out in the summer, and I started that by making a set of scanners and parsers to allow the input of an agreeable representation of data that one may want to test, and that is using basically graph notation instead of being reliant on knowing Pythonic data structures. So we'll take a look at that right here. So I'm going to open up some documentation and take a look at these schema notes right here, and we could get a good glimpse of the important pieces of the input data. I should move this down too. We have a population graph, and as you can see for this, within this first line of BNF notation, it is basically what we studied in the data structures class. We have a set of edges and a set of vertices, right? And we also have a transition set, which sort of describes the transition function to be used within a population. We also have an initializer set, and this set sort of primes the states of the agents, because if you recall from data structures, each vertex that exists within a graph needs to have a unique identifier. So the initializer set is a means to sort of get those states into the graph proper, into the population, into each agent. So let's make a simple graph. For starters here, make a set of files, which is called test.graph. This will, I already have one there. Let me Let me just delete these. Let's do a test.graph. And let's make a simple, fully connected graph with let's say 4 nodes. So we have A, B, C, D. So there's our vertex set. Let's get a set of edges. We got A, B, B, A, C. I forgot a comma. A, C, C, A. Getting these all connected. B, C, C, B. We also need D in here, so A, D, B, D, C, D, D, A, D, B, D, C. Make sure I have a comma. Close up that set, close up the grouping. Alright, so we have the test graph right here. Looks alright to me. Yes. Let's make a initializer set now. Test.init. Okay. Let's set A, B, and C to the state of 0. Close that up. And let's set D to the state of 1. Let's close that up. Save it. Let's get a transition function in place. I'm just going to copy and paste this one. Use the same transition. Bam, there we go. Alright, hopefully I have the syntax here correct. If not, it will error out. So let's run the population protocol simulator. Whoops. Put test.graph. Whoops, looks like we got something wrong here. That's because I put in the wrong name here, test. There we go. We're expected to converge on value 1, and I am just going to print the graph as is before any interactions. Whoops, wrong folder. So let's do a print. And here we go. Here we have our graph. So what it looks like, that's kind of what's expected, right? Based on what we input for the graph file right here. You probably would think by now that it could be pretty cumbersome to force someone to sort of input each of these edges as is. And to be honest, you would need if you have a pretty large graph or a population you're working with, you would want to programmatically sort of build that. But I did add some syntactic features to the population graph to make that a bit easier for the user. So I'm going to exit out of this. It's going to clean up. And you'll notice that within the population graph, we have the notion of an ordered pair and an unordered pair. So let's just go back here. I'm just going to delete some of these for brevity's sake. So we have these two edges right here, AB and BA. These are two ordered pairs, as I call them within my BNF notation here. There's also the unordered pair, and basically this tells the simulator to have a two-directional means of communication. So let's run it again. Python 3 protocol runner print. And here we go. We see that it did in fact output that. So now we have a syntactic abstraction in place. Furthermore, you may want a fully connected graph. So instead, the user could just have an empty set of edges, and the simulator will assume that you want a fully connected graph. So let's run the protocol again. Let's print that graph. And here we go. Here it is. So let's start running some let's start doing some interactions here, right? So within this simulator, we can run an interact command. Let's do one interaction. I don't know if anything will happen, so let's print. So the regular print command will simply output the new state after a simple interaction, and it will show interactions in which a state has changed, right? So as you can see, here's the first image, and I'm going to change to the next graph. Nothing happens, but that's because a null interaction happened. So I'm going to do a null print, and now we're going to look at that null interaction, and it looks like it happened between these two agents. Nothing occurred. So I also have a command within the simulator. If you were reading, you can input 0 to interact until a state changes. So let's do that. I'm going to exit out of this. Let's put in 0. And let's print that. And the first interaction that occurs happens between as D is the sender and C is the receiver. And we could sort of walk through the convergence of this population by using these commands. I'll just do a couple right now. Interact 0. And it looks like it has converged, and it happened on this step, right? So I forgot to print them, but yeah, we can see these are the means of communication that occurred right here. I'll do another null print so you can see the potential bottlenecks and whatnot that happen. These are where the null interactions happen. I'm not sure if you can tell, but the thickness of the lines change dependent on the amount of interactions that happen along the edge, and so does the vibrancy of the color. So let's look at a larger population. All right, I'm going to exit out of this. I'm going to exit out of this population. It's going to clean up. Take a look at our input files. Let's do. I have another set of populations in place. We have this simple OR population. So here we go. Oops, that's a transition file. I meant to open up the graph file. Here we go. It's simply nodes from A to I, agents from A to I. We initialize every agent to the state of 0, and we initialize I to have the state of 1 when it runs. And the transition function is the same as before. It's the one-way, in terms of a population protocol, it's a one-way communication OR statement. So let's give this a run. Simple OR. Expect it to converge on 1. Let's give a good old print so we can see the initial state of things. Go back to the output folder. Here's what it looks like, right? So let's interact until a state changes, and just print, interact until a state changes, print, interact, and so on, right? So here's what the first set of interactions look like. This is the path the value has taken, if you will. You can see that the value of agent F has changed to 1, right? And so on. It looks like B is changing to 1 also. Let's do a null print so we can get a good idea of the null interactions that occur between agents along the edges. This is what it looks like. Looks like it's sort of centralized, if you will, but that's arbitrary, right? The positioning. And I also have a convergence command. Looks like it has converged onto on step 32, rather the 30-second interaction. Should probably change the output. Let's do a print so we can get an idea of what the path was as this execution occurred. There you go. This is how the value of 1 propagated throughout the population. Let's do a null print, because it's pretty cool. And this is the amount of null interactions. Rather, it's a graphical representation of like the ratio of null interactions. I don't have actual values being output along the edges, which is something that I can easily do. As we can see, it looks like Agent A was the sender for Agent E more so than other nodes. All right. Of course, I just want to re-emphasize on the fact. Let me exit out of this. I want to re-emphasize on the fact that restricted graphs are also game. Let's take a look at this input. I have a restricted graph right here. This is not a full set of edges right here. Let's do restricted OR for our graph. Let's print this. Go back to our output file. There it is before any interaction. We could sort of guess what's going to happen. It's just going to walk its way up through these nodes. I'll just do the first interaction. Interact 0 print. Yeah, it's pretty expected, right? We'll do null print right here. A lot of null interactions have occurred because no states were changed, right? So I'll converge here. All right, converges on step 65. Do a print. Here's the path. We expected that, right? And this sort of represents the strength of the null interactions. All right, and I'll give another example here. We have this majority graph right here. We have a set of nodes. It's fully connected, hence this syntax. Just over half of them are instantiated to the value x, and under half of them are instantiated to the value of y. Here's the transition function. Basically, this population protocol sort of approximates the majority of the majority value of a population. Mind you, it's not always 100% accurate, but the larger the discrepancy between values, the difference of values, I should say, it's more accurate. So let's see what happens when we run this one. So I'm going to put in the majority as the population name. This should be X. So let's do a print so we can take a look at it initially. This might be a bit too big. We'll find out. We'll find out. Yeah. So we got it. It's pretty busy, right? We got a set of nodes. Some of them are X, some of them are Y. I'm going to interact until a state changes. I'm going to print. Let's take a look at it. Looks like the vertex M, rather the agent N, communicated with agent C. C must have had the value of X. Thus, it changed to B based on the transition set rules that are set in place. Let's see what the null print looks like, if there were any. Doesn't look like there were. So let's do a random amount of interactions, I guess. Interact. Let's do 50 times. Print. See what it looks like. These are all the interactions that have occurred since then, and you can tell it has not converged yet, right? Because Y or X has not dominated the population in terms of their states. Kind of looks like, yeah, I'm not sure what will at this point in time. But we can see the communication from agent D to agent A is pretty, like, it's happened a lot in that regard. Mind you, remember, this is just regular interactions that do indeed change the state of the configuration of the population protocol. So you can tell that there's weights to them also. Likewise, I can also do a null print, so we can take a look at the the amount of null interactions that occur between the states. So this is the same configuration. What we're looking at is the regular interactions, and these are the null interactions. So once again, that can sort of emphasize on that can sort of show us that we can perhaps look at potential bottlenecks with the various algorithms that we're looking at. So I'm just trying convergence here for the fun of it. Let's do 500. All right, looks like it converged on step 135. So X did indeed dominate. It did propagate throughout the population. So let's do a print. We can sort of take a look at the various interactions that occurred, and we can see that, yes, all the agents do have a value of X. And let's take a look at the null print option here. Whoops. Yeah, let's do them side by side, huh? And we can sort of contrast the two. On the right is the regular interactions, and on the left are the null interactions that occur. So yeah, that's the gist of what I've been working on. Making a set of parsers and scanners for the input data of this simulator. Here they are. I'm just sort of highlighting them. I have superclasses, whatnot, etc., etc. I've also, like I mentioned, I sort of rebuilt things, so I applied a more object-oriented approach to this, something that's easier to look back. I guess I'll show you the original simulator as is. It's kind of rough. It's pretty rough. It's pretty ad hoc, like I said. This is what I like to show people. To be honest, I hate this kind of indexing that I employed here. We have this agent map at index I of index k. I don't like doing that. So I took a break after working on this initial simulator, and I came back to it and I looked at it as basically I thought to myself, what the hell was I thinking, right? So I started from scratch this fall. We have the parsers and scanners in place. Luckily, the compiler's course really pulled through me in that regard. I have a population protocol class, which uses a class of agents and whatnot. Within this population protocol class, we have a check for convergence method. We have an invoke interactions method, etc., etc. Something that prints something out too. We have a render configuration. So if you were paying attention, you notice that I'm outputting DOT notation for these graphs. So here's the first one that we output. Here's the second one, and within it you can sort of see that the values are dynamic based on the strength of the edges that I want to be printed. And as you could probably tell, as you've probably thought, that this command line user interface is kind of cumbersome. It's kind of tedious having to type in interact and print and null print and whatnot. So eventually I would like to have a graphical user interface for this. And another piece of this code that I have been working on but is not quite ready to show yet is the concept of an interaction log. And basically this keeps track of each interaction that occurs, whether or not it's a normal interaction or a null interaction. And basically I have methods in place to allow one to roll back to a previous configuration or previous state of the population before what's currently happening. And from that they can restore back to the original. So within the graphical user interface, I would like to have some sort of slider that allows the user to sort of seek through the previous iterations of a population. I do have something in place that sort of rolls back. My rollback function does work for the most part. There's one quirk to it. So I'm going to do a rollback command right here. This is just sort of, this output exists for me to work through my logic. This first grouping right here is basically the interaction counts in which a null interaction happens, but the second one is just regular interactions in which state does change. So I'm going to roll back to state 1, all right? And we're going to do a print, and it should be very sparse. Yes, it is. So you can see that something's in place there. So yeah, that is the extent of the work I've been doing. Hopefully has been mostly coherent for you. If you have any questions pertaining to what I've done, feel free to shoot me an email. Thank you.